Here we are on part 2. We're going to continue with our problems, 10, 11, 12, and 13 from our study questions. Now this one we're not going to spend much time. Okay, what do we have? We have at 375 degrees, okay, the Kc is 0.045. So we know Kc. So we're talking about concentration of SO2 times concentration of Cl over the concentration of SO2Cl2. Okay, what's the value of the reaction quotient? Is the system at equilibrium? And which direction will the system move to reach equilibrium? Well, the only different thing on this one than our other problem is that this time we're talking about grams and grams and grams of our three chemicals. So all I can say is you're going to have to change each one of these to moles, moles, and moles, and it is a 1 liter container. So before you substitute numbers in to get our Q, then we're going to have moles divided by 1 liter, so molarities. Now, that's a very simple task. I think it's a little bit just another extra step you have to do, and I'm just going to leave that for you to look at. So change the grams to moles using the molar masses, and you have to figure that out for each chemical, and then put them in and compare Q versus K. Now number 11, this is a slightly different kind of a problem. And what happens here, we take a little bit of ammonium chloride, which is a white crystal, and you're going to put it inside of a closed container. And what happens with this solid then is that it can start to decompose, and we'll get two different products up here. Okay, we're going to get some ammonia, and we're going to get some hydrogen chloride gas. So our original chemical is going to decompose into these other two gases. So we can start off with just what we think we need to do. Let's go ahead and draw an ice box. And we're given that there's a Kp for this system. So the Kp will be the partial pressure of NH3 times the partial pressure of HCl. Now HCl, if we saw that as a solution, we'd say that's hydrochloric acid, but as a gas, it's hydrogen chloride gas. Very, very terrible thing to smell. If you have concentrated hydrochloric acid in a bottle, HCl is what goes up into your nose. Now this is all equal to 0.640. So we can see what happens is, here's a solid, so we're just going to totally ignore that. Okay, we don't need it for our calculations. And we're going to say, well, we're not putting any of our gases in. We started with just the solid down here in the bottom. So these are 0 and 0. And what we're trying to do is get pressures. So we're going to do these all with, I would assume that these are going to be atmospheres. So we're going to go, this must be forming some of this, and we must be forming some of that, because the reaction has to shift to the right, because there's no product in order to shift to the left, so it has to go to the right. So we're going to make X amount of each of those, so at equilibrium we'll have X and X. We substitute it in, so X times X equals 0.640, and it looks pretty obvious. We're going to have X squared equals 0.640, take the square root of both sides, so X equals the square root of 0.64. So that's easy stuff. Now, what I would like to point out here is, what is the question asking? What is the pressure inside the vessel? Now, I know for myself that I would get to the point where I say, okay, X squared is equal to 0.64. I'm going to take the square root of that. So X equals the square root of X squared equals the square root of 0.64 equals 0.800, and I'm going to say that's atmospheres. And I would be so excited to have my answer. I can say, there, I'm done. Let's go on to the next problem. And I would get it wrong, because that's the partial pressure of my HCl, and it's the partial pressure of my NH3. So if I have both of those gases mixed up in my container, the total pressure is going to be 2 times 0.800. So my actual answer that I would want to report is 1.60 atmospheres And so this is not a difficult problem, but I really want to point out is be sure and answer the question that is given in the problem. Don't just solve for x, answer the question. Now, I'm done. Number 12. Bromine and chlorine react to produce bromine monochloride according to this equation. Under the conditions, there's the equation. If 1.8 moles of bromine gas, 0.18 moles in chlorine gas in a 3-liter flask. So we can already see then what's going to happen is my concentration of bromine is going to equal my concentration of chlorine, and they are both going to equal 0.180 moles over 3 liters. So that's going to be 0.060 molar. So that's going to be a useful number there. Okay, I'm going to go back and put that into my expression. So let's make an ice box. And I have two questions in this question. And one is, what's the equilibrium concentration of the bromine monochloride? So I want to know this value. So I'm going to say this is 0.60. Let's double check that. 0.060. So 0.060 molar, 0.060 molar, and 0 molar, because none of that was added. And we can see what we're going to do is we're going to say minus x plus 2x. So be careful about that 2. And so this will be 2x. This will be 0.060 plus x and 0.060 plus x. Now, my equilibrium, I get to solve for my x. And you can see what's going to happen when I put it back in my expression. I will get 0.2x squared on top, and I'll get these guys multiplied together on the denominator. So I'll go back here and say here it is, Kc. So the Kc is equal to concentration of BrCl squared over Br2 times Cl2, and that equals 2x squared over, and it's 0.060 plus x. Is that plus x? Okay, this shouldn't have this wrong. This should be a minus x. I'll do it in red. This should be minus x, and that should be minus x. That should be minus x. The other one's plus x. Okay, so 0.060 minus x squared, and that equals 36. Now, at this point, it's probably obvious. Okay, squared, squared, so I can square root both sides of my equation, and I can solve for x. Now, that I'm leaving for you. My point here is, what's the question? What's the equilibrium concentration of the bromine monochloride? So when I get my value, I need to double it, and that's my first answer. Then you say, how much BrCl is produced? Well, when we get an answer here, we're going to have a concentration. So if I say, and I'm just going to make this up and say that it came out to be 0.300 molar. Okay, well, I'm going to take my concentration multiplied by my volume, 3.0 liters, because this is moles per liter. When I multiply those, my liters drop out, and I will get the answer to how much BrCl is produced, and that'll give me a mole answer. So the idea is, don't just stop at x. In this case, I had to double the x, and then I had to do a calculation using molarity and volume to give me the moles. Now, if they really wanted grams here, I think they would have said what mass of BrCl2 is produced, or we could also just go on and tell how many grams this is as well, if we're not quite sure what they want. Okay, this last problem goes back to some things we did over the summer, and the idea is, remember, we were testing household products, and one of the ones we tested was ammonia, and we found out that when we tested it, okay, we added a little bit of cabbage juice to it, and we kind of ended up with a blue-green color for our cabbage juice. Okay, so it was definitely a base. And it made sense that this is a base because of the idea that we can see we have hydroxides being formed. But for most bases, the idea is that there's an OH in the solution, like sodium hydroxide, magnesium hydroxide. Those guys would be strong, just nice bases. But the other thing is that when we tested this with a light bulb, then we found out that the light bulb did not burn very brightly. Okay, it went on, but it wasn't a bright light bulb. It was a weak electrolyte. So we decided here that what's really going on is there's ammonia, and that the ammonia reacts with the water, and I'm drawing these large on purpose, and it breaks up and we get a small amount of ammonium ions and a small amount of hydroxide ions. I'm leaving out the aqueous just for space. And the reason we have a small number of those is because there is a tendency for those ions to join back together to be ammonia and water. And when the equilibrium is established, we have small amounts of these two ions and we have very large amounts of these two chemicals. So we say it's very reactant favored. And we know that as well if we look at the value of the constant, 1.8 times 10 to the minus 5, that's much smaller than 1. So when we take the concentration of the products divided by the concentration of the reactants, then we get a very small number. So I know that this is a base because I have hydroxides. I know that it's a weak base because the equilibrium really emphasizes the reactants, not the products. So I don't get very many hydroxides. Now we come back to our equation. We'll do an ice box. And this one is going to illustrate one more little algebra trick sort of thing we can do. And going back, look at the problem. We have a 0.1 mole of ammonia in a 500 milliliters of solution. So we have 0.100 moles of ammonia in 0.500 liters. So we can see that that is going to be a 0.2 molar solution of ammonia. Now, we're going to start off here, change color, 0.2 molar. Here's a liquid, so let's cross that out. We're not even worried about those values. And we didn't start with any of our ions. All of this, nothing was added. So we can see what we're going to do is we're going to say this is minus x, plus x, plus x, x, 0.200 minus x. Now, we go back and do our expression, and we have a value for the Kc. It just says equilibrium constant, so we're going to assume that's a Kc. So Kc equals the concentration of ammonium times the concentration of hydroxide over the concentration of ammonia, and that equals 1.8 times 10 to the negative 5. If I substitute in my values, I get x squared over 0.200 minus x equals 1.8 times 10 to the negative 5. And you can see what's going to happen is that this is going to turn into a quadratic equation. I'm going to have x squared, I'm going to have x, and there's one little thing we can do about that. And that is, we're saying that X amount of this chemical dissociates, breaks up into ions. But that's not very much compared to the original amount. In fact, this here is my picture kind of shows my reactants as maybe 4 or 5 times larger than X. It's really more like 100 times larger than X. So if we did not subtract this X in this case, that would not cause much of an error in our answer. Now, these X's, these are very important because if I multiply by a small number, okay, that makes a big difference to my answer. But if I don't subtract a small number compared to 0.2, that really will not change my answer very much. So let's go back. And when we do this, we are not going to try to sneak anything by. We're going to be very above board about this. So we're going to say assume that x is much smaller, 2 less than, is much smaller than 0.200. And we'll come back and talk about why we can make that assumption, or how do we know that that's a good assumption. And therefore, 0.200 minus x is about the same as 0.200. Now that changes our question down here quite a bit. So now we can say, let's ignore this. Let's pretend that that x is basically 0. So x squared over 0.2 equals 1.8 times 10 to the minus 5. Multiply both sides by 0.2, and then take the square root, and we get a value for x. And that value comes out to be 1.87 times 10 to the negative 3. If we went back, and we only have 2 significant figures because of this, so we would call that 1.9 times 10 to the minus 3. If we went back and used the quadratic, we find out we get 1.88 or 1.89 times 10 to the minus 3. So to 2 significant figures, we still get the same answer. So when we have a situation, let me get a new color here. When I have a situation where this number compared to this number, our k, when our k is like 10 to the third times smaller than the 0.2. This is 2 times 10 to the minus 1. This is 2 times 10 to the minus 5. So that's 10 to the fourth power smaller. So when I get a situation where this is much smaller, 10 to the 3 times smaller at least, then this x is so small that we can ignore it by using this little statement along the side, and the solution of that math problem becomes much, much easier. Now those are all the problems that we have about these study questions. So part 1 and part 2 cover everything that has to do with ice boxes on these study questions. Thank you.